So the topic is design of building retrofit by isolation system and its displacement restraint mechanism. And my name is Lin Pengyu. So we will start from the outline. The first part will be the introduction, and the second will be the isolation retrofit design, and the third will be the retrofit of DOT to an elementary school. And the fourth will be the displacement restraint mechanism. And at last will be the conclusions. So there are two important topics in my thesis. The first one is the isolation retrofit. So why do we use the isolation to retrofit our buildings? We will discuss later. And the next important part will be the displacement restraint mechanism. So this part will be the introduction. So as we know that the structure's seismic capacity decreases as it ages, and also after GG earthquake, seismic demand was increased based on the seismic design code. We know that for a retrofit of the structures, there are some conventional retrofit methods such as shear wall, wing wall, bracing, or concrete jacketing. But however, these kind of conventional retrofit methods may change the structure's appearance. So actually for historic building, these kind of method is not suitable. So the seismic isolation system is introduced in my thesis and used to retrofit the building. So how does the isolation system work? You can see from the spectral acceleration that the period will increase and the damping ratio will increase too, and the demand will be reduced. And also for the displacement spectrum, the displacement response will be decreased by the increasing damping ratio. And thus by these methods, the goal of retrofitting can be reached. So is there any practical example in the world? So there is one in Japan, which is the Yamanashi Prefecture Municipal Government. So this is a 8-floor building. It used for the construction, the temporary supporting system based on post-tension units are used. And we can see on the right picture that this is the seismic isolation retrofit completion, and lead rubber bearing is used as the isolation system. So next part will be the design range. So what is design range? The concept of the design range is introduced in my thesis. So once we choose the design parameters in this design range, the result is promised to be an available design. So we know that for the original isolation design, first we will choose the design parameters, the period and damping ratio. And next we will draw the design spectrum and then find the design displacement. And then the system design is the system design. So we have to determine the parameters of the isolation system. And once we have the system's parameters, next will be the detailed design. So the actual parameters of isolation system will be determined. The result, then we will check the design result to check if the design displacement is exceed allowable displacement, or the demand exceed the capacity or not. So if the result is not okay, we have to choose a new value and do the design procedure repeatedly again. So if it is okay, then the design is finished. So for the original isolation system, we have to do the procedure repeatedly. So for a more efficient way, we provide in my thesis another logic that we use all the design targets to set a design range. So the parameters in this design range is promised to be a okay design. So this is the isolation retrofit design procedure. So first part will be the seismic evaluation. And RCD is the capacity to demand ratio. So after the seismic evaluation, if RCD is bigger than 1, it means the structure don't need retrofit. But if RCD is less than 1, have to go through the retrofit design procedure. First is setting a design goal. Next is find the design range of the isolation system. So there are two isolation systems used in my thesis. The first one will be the friction pendulum bearings, and the second one will be the lead rubber bearing. And for the design range, the two important parameters for FPB is mu, friction of coefficient, and R, radius of curvature. And for LRB, it will be QD, the characteristic strength, and KD, the post-yield stiffness. Once we have defined the design range, we have to choose the parameters in this range. After the system design will be the detailed design, and at last we have to check the design. So design range is just look like the figure on the right side. So for the X and Y axis, it will be the important parameters of the two isolation systems. So the first part will be the seismic evaluation. So for seismic evaluation, it is provided by INCRE, the Manual for Seismic Evaluation and the Retrofit of School Buildings, 3rd edition. So the nonlinear pushover analysis is used to do the seismic evaluation. And the pushover analysis is used in the software such as MIDAS, SAP 2000, or ETAPS. So how do we do the seismic evaluation? First, we have to build the structure model and assign a linear plastic hinge to the structure. And second, we will carry out the pushover analysis in the software. And third, after the pushover analysis, the pushover curve is obtained, like the right side. And by the pushover curve, the performance point is determined, and then the seismic demand of the structure is obtained. Next, by the structure's location, the seismic demand will be determined. So RCD, the capacity to demand ratio will be determined. So this is the example structure. This is an hypothesized example structure. So it is located at Sui Hualien. Its site classification is soft type. And from the location, SDS and SD1, the value are determined. And this structure is an emergency shelter, so the importance factor I equals to 1.5. Also, we know the structure slab thickness is 15 centimeters. Its beam and column section size. So the structure weight is obtained. W is 75.6 ton. The steel yield strength Fy is 3,200 kgf per cm square. And the concrete strength FC plumb will be 190 kgf and cm divided by cm square. We know that it is a weak concrete strength. So this will be the pushover results carried out by the pushover analysis in ETAPS. So for the left figure, it is the pushover curve. So since this structure is an emergency shelter, so the capacity is chosen to be 80% of Vmax. And by the manual of retrofit of school buildings, for this point, 80% of Vmax, the corresponding spectral acceleration SA is determined. Once we have SA, we can calculate the RCD, which is SA divided by the demand, SAD, which is equal to 0.4887, which is less than 1. So it means that this example structure needs to be retrofit. Next will be the FPB retrofit design. So first part, from the basic information of the structures and the relation of the parameters, first step will be finding the B1 and TE range. And next part, the B1 and TE range can be changed to the damping ratio and the TE period range. And for the last step, from the damping ratio and TE range, the mu and R range is determined. So by choosing the parameters in the mu and R range, the system's parameters can be determined. So the first design range will be the B1 and TE relation. So by our design goals, we can find the conditions and then find our design range. So first design goal will be the shear force have to be less than the structure's capacity, EBS. And the corresponding condition can be determined. And for this condition, the first design range is the blue color area. And the second design goal is that the design displacement have to be less than the allowable displacement, which is set to be 45 centimeters here. So the relation, the second relation is determined. And for the third one will be the isolation period. It has to be between 2 to 5 seconds. And the fourth one, we know from the seismic design code of buildings that the value of B1 is between 0.8 and 1.75. So by these four conditions, the available range of B1 and TE is determined. And by the points on the boundaries, we can find its corresponding value of theta. So the x-axis remains the same, but the y-axis value have changed. So the damping ratio theta corresponding to the value of B1 is determined by the seismic design codes table using the linear interpolation. So by the boundaries of the points on the boundaries of the last figure, we can find the corresponding points on this figure, and thus get the zeta and TE design range. And next, we know that from the left side picture, it is the friction pendulum bearing. Friction pendulum bearings force and displacement relationship. So by this relationship, we can get the relation of some parameters. And by these equations, we can solve for the two unknowns. The first one will be the friction of coefficient mu, and the second will be the radius of curvature. So mu and R are shown on these two equations. And we can see that there are two unknowns, which is zeta and TE, in these two equations. So by the last figure, the value of zeta and TE can be input into these two equations, and thus the value of mu and R will be determined. So then by the last figure, mu and R design range will be determined as the blue color area. We also know that from the FPB on the market, the radius of curvature is usually between 1 meter to 6 meters. And the value of friction of coefficient is usually between 0.02 to 0.06. So this orange line will be the final design range. And the point is chosen is in this range that R equals to 4 and mu equals to 0.04. This will be the system design's parameters. And next, by the system design's parameters, we can then do the detailed design. So we know that the system design result R equals to 4 and mu equals to 0.04. The value of damping ratio, design displacement B1, period, and the total number of FPB is determined in this table. So this will be the diagram of an friction pendulum bearings. So it consists of an articulated slider which its radius will be small r. And also there is a spherical concave curve on the bottom. And between the slider and the concave curve there will be a bearing material. And at the boundary of the concave curve there will be a stopper. So for a single friction pendulum bearing, we know that the actual load will be 33.2 tons for a single FPB. And we know that we have to find the parameters of the FPB that for the articulated slider, we know that its material is usually used, the type 304 stainless steel is usually used. And for the bearing material, Teflon PTFE is usually used. And we know the yielding strength for these two kind of material. So for the actual load divided by the section area, which is the stress of this section have to be controlled by sigma y and sigma y plumb. So it is usually controlled by sigma y plumb, which is the Teflon. So by these conditions, R have to be bigger than 4.99 centimeters is determined. Therefore, the size of the FPB will be determined that since the ultimate displacement du is 50 centimeters, the stopper's length L is 0.6 centimeters, so the diameter of the concave curve phi will equal to 2 times du plus R plus L, which should have to be bigger than 120 centimeters. So this will be the detailed design result of the example structures FPB. And at last, we have to check the design. So we have to simulate the friction pendulum bearings in the E-tabs. So there are two methods. The first method will be using the nonlinear link property isolator 2. And the second method will be using a nonlinear plastic hinge to simulate FPB. So we can see from the nonlinear link property that for the input, the frictional coefficient is equal to 0.04. And for the radius of curvature, it will be 4 meters. And for the nonlinear plastic hinge, we use the force displacement relation to simulate the FPB's theoretical force and displacement relationship. So we can see from the results that we draw the shear force corresponding to the isolation displacement. And this figure is drawn according to the force displacement relationship of the friction pendulum bearings. So the black dashed line will be the theoretical value, and the blue line will be the result of the link property, and the orange line will be the result of the nonlinear plastic hinge. So we can see that these three lines are very close. So we can say that the simulation is quite well. So we want to see the relation of the shear force according to the roof displacement. And we push to the design displacement, and by this point, the corresponding shear force V can be determined by this pushover curve. And the value of V can find its corresponding value spectral acceleration, SAD. And after the retrofit, the RPV will be the SA divided by SAD, which is now equal to 2.29, which is bigger than 1. So we can say that this is a successful retrofit design. And we also want to check if our pushover curve is reasonable or not. So we want to compare the structure's elastic stiffness. So for the first picture, it is the pushover curve of the original structure, and the second figure will be the FPP retrofit structure's pushover curve. So by on the two orange line, it will be the elastic stiffness, and the first will be 649.3 ton-meter, and second will be 637.9 ton-meter. And these two values are very close, so that we can say that our pushover curve result is reasonable. Next is the actual structure that we use to do the retrofit design procedure. So this is the Datun Elementary School. So actually this structure is a one-floor building. It is located at Beitou, Taipei. However, this structure RCD is bigger than 1, and it means that it doesn't need to be retrofit. So we changed some of the structure's basic information. That we turn the structure into a second floor building, and we change its location to Jian, Hualien. So its site classification is soft type. Its value of SDS and SD1 is determined, and the structure weight is 664 tons. The slab thickness is 15 centimeters, and tau F, the force between the brick and the mortar, is equal to 2.84 kgf per cm square. And it is an emergency shelter that I equals to 1.5. And this structure is made of brick. So the first part will be the seismic evaluation of the brick structure. So how do we do the seismic evaluation of the brick structure? This is a brick wall, and its section area will be AB, which is equal to its thickness WB times its length TB, and its stiffness will be Vn divided by delta U. So we use an equivalent column to simulate a brick wall, and we assign a shear nonlinear hinge to this column to simulate a force displacement relation of the brick wall. So for the equivalent column, its section area is A, and its stiffness is GA divided by 1.2H. So once we build a brick wall in ETAPS, we have to change its section area so the stiffness will be the same. So what is the reduction factor RA? It will be the column section A divided by AB, which is equal to this equation. So by assigning the reduction factor RA to the brick wall section, the equivalent column is determined. And after the seismic evaluation will be the friction pendulum design procedure. So first, the design range of B1 and TE will be determined, and it can be changed to the damping ratio and TE design range. And last will be the mu and R design range of the Datun Elementary School. So by choosing the point in the available range, that R equals to 2 and mu equals to 0.06, the FPP system's design parameters are determined. So for the system design result, we can see the damping ratio, the design displacement, the value of B1, and the period TE are determined, and the total number of the friction pendulum bearings will be 10 for Datun Elementary School. And the right side shows the detailed design result for a single FPB. So for the single FPB of Daton Elementary School, its actual load is 1,071.8 tons. And the radius of the articulated slider R is equal to 10 centimeters. And the ultimate displacement du is equal to 50 centimeters. The stopper's length is 0.6. So at last, the diameter of the concave curve is 130 centimeters. And the next part will be the design check. So we can see the left figure will be the original pushover curve. And the right side will be the friction pendulum bearings, will be after installing the friction pendulum bearings pushover curve. So before retrofit, the RCD will be SA divided by SAD, which is equal to 0.411, which is less than 1. It means the Daton Elementary School need to be retrofit. And after the retrofit, RCD is now equal to 1.47. And it means that it is a successful retrofit design. Next part will be the displacement restraint mechanism. So this displacement restraint mechanism is used to restrain the isolated structure's displacement response. So what is this kind of system? It is made of a spring and a damper. And where will it be situated? It will be between the isolated structures and the retaining wall. So why do we want to design this displacement restraint mechanism? So since earthquakes are unpredictable and there are chances of near-fault earthquake happens, so isolated structures have a chance of collapsing. So we know that dampers are usually used to restrain the displacement. But actually dampers are part of the isolation system. But the displacement restraint mechanism we introduced is independent of the isolated structure. And also for the retaining wall, once the isolated structures hit the retaining wall can be hard to be repaired. So the displacement restraint mechanism is necessary. And how do we design? So first we have to determine the design parameters, and then the design procedure will be determined. And at last, a design range will be obtained. And the picture on the right side will be the TMD's displacement restraint mechanism in Nanshan building. So this is the schematic diagram of the displacement restraint mechanism. So for the original isolated structure, it is its mass M, its structure stiffness K, and its damping coefficient. And K1 and C1 are the displacement restraint system's stiffness and the damping coefficient. And there are also some important design parameters. The first one will be dA, which is the isolated structure's allowable displacement. And the second part will be du, the isolated structure's ultimate displacement. Once the structure's displacement response have exceed this value, it means that the structure is very unsafe at all. And dm will be a trigger distance. Once the displacement response exceed dm, it will hit the displacement restraint mechanism. So how do we simulate this kind of system? So there are two assumptions: that we assume this structure is a SDOF structure and it is a linear system. So the following will be the equation of motion of this total system. It will be mx double dot plus cx dot plus kx equal to f minus mxg double dot. So f will equal to 0 once the displacement response is less than dm. And f will equal to this once x exceed the value of dm. So how do we design the displacement restraint mechanism? There are three important parameters. So also we want to use a normalized value that we use alpha 1 and alpha 2 to represent K1 and C1. So alpha 1 will be K1 divided by K, and alpha 2 will be C1 divided by the original structure's damping coefficient C. And dm, the third is the dm trigger distance. So this is the example structure, FPB retrofit example structure that we discussed previously. So for this structure, we already know that the ultimate displacement is 50 centimeters, the period is 3.37 seconds, and damping ratio is 18.67%. So the time history we use is the Hualien earthquake on February 6, and the station will be HWA 011 north-south. And this earthquake's PJ will be 199.2 Gauss. So we can draw the corresponding spectral acceleration and displacement spectrum. So we can see from the acceleration spectrum that for this FPB retrofit example structure, its maximum acceleration will be 200.1 Gauss. And for the displacement spectrum, we can see that the maximum displacement response will be 53.98 centimeters. We can know that Dmax is bigger than the ultimate displacement du, that this structure have to design a displacement restraint mechanism. So we can see from the simulation result that the displacement will decrease due to the impact, and simultaneously the acceleration response will actually increases due to the impact. So there are some design targets that we have to satisfy. So first one, after installing the displacement restraint mechanism, the displacement response is hoped to be less than the ultimate displacement, du equal to 50 centimeters. And the acceleration response have to be less than AU, which is 350 Gauss. So 350 Gauss is determined by the structure's shear demand. So once the acceleration response have exceed the value 350 Gauss, the structures may endanger. And how do we do our design? So first, for this FPB retrofit structure, we have to use a linear system to simulate. So for this structure, its mass will be 100.6 tons, and its stiffness K will be 418.6 kN divided by M, and its damping coefficient C will be 83.91. And next part will be designing the value of alpha 1 and alpha 2. So how to design alpha 1 and alpha 2? So first, we want to discuss alpha 1 and alpha 2 separately. So first, if we use spring only as our in our displacement restraint mechanism, so we can draw the normalized displacement response due to the value of alpha 1, and the normalized acceleration response corresponding to the alpha 1 value. And we can see that the displacement response have decreased once the value of alpha 1 increases. And acceleration response will increase according to if alpha 1 value increases. And similarly, if we use damper only as the displacement restraint mechanism, we can see that the displacement response will decrease and the acceleration response will increase as the value of alpha 2 increases. So we can see from this slide that if the value of K1 and C1 is bigger, the displacement response can be restrained more effectively. However, the acceleration response will be big, that it also have to be noticed. So we want to use damper and a spring as our displacement restraint mechanism. So for a combination of a damper and a spring, there will be combinations of alpha 1 and alpha 2. So we want to draw a 3D diagram that the x-axis is alpha 1 and the y-axis is alpha 2. And by the combinations, we can draw the displacement and acceleration responses. So this will be the 3D diagram. And from the left side figure, it will be the displacement response. The z-axis will be a displacement response, and x, y are alpha 1 and alpha 2 respectively. And from the green color plane in this area, it will be the design target, du equal to 50 centimeters. So the points under this plane will be an available design combinations of alpha 1 and alpha 2. And the right side will be the 3D diagram of the maximum acceleration. So also, AU equal to 350 gal will be the design targets. So for the points under this plane, it will be the available design combinations. And we want to simplify these two 3D figures into the contours, which is shown below. So for the contours, the x and y are alpha 1 and alpha 2, and for the labels on the contours, it shows the value of the maximum displacement and the maximum acceleration. Next, we want to normalize our contour figures, that if we divide it by Dmax, by the design target, du 50 centimeters, and Amax divided by AU equals to 350 gal, we can get the normalized value. And after we get the normalized value, it is important to find the normalized value equals to 1. And the left figure will be the displacement design range, and the right side figure will be the acceleration design range. So for the yellow color area, it will be the available range, which Dmax divided by du is less than 1. It means the combinations in this yellow color area is promised to be an okay design for the displacement. And the yellow area in the right side figure is the Amax divided by AU will be less than 1. So if we interpolate these two figures together, we can find the intersection, the yellow color area. And for the color area, it will satisfy the displacement G divided by du less than 1 and Amax divided by AU less than 1. So this will be the available design range of the FPB retrofit structure, which satisfy these two design targets. And this will be the final design range. And we want to check if this range is okay, that we choose a point in this area that alpha 1 and alpha 2 both equals to 2. So for this alpha 1 and alpha 2 equals to 2, we will draw the displacement and acceleration time history. So the orange line will be the original structure that without the displacement restraint mechanism. And the blue line will be the time history after installing the displacement restraint mechanism. So we can see from the displacement response that the original displacement is 53 centimeters. And after installing the displacement restraint mechanism, its displacement response is successfully decreased to 47.176. And for acceleration after installing displacement restraint mechanism, the acceleration increases to 310.6 gal, but actually it doesn't exceed the structure's capacity, 350 gal. So this will be an available design. And next, we want to discuss about the design range, that if we change our design targets. So we can see from the figure on the upper side that if we change the acceleration targets, that the displacement target remain the same. We change the AU from 350 gal to 300 gal and 250 gal. So by these three different acceleration design target, we can see that for the AMAX smaller than 350 gal, the design area will be the blue area, including the red area and the yellow area. And for the more strict AMAX less than 300 gal, the design range will be orange area plus the yellow area. And for the AMAX less than 250 gal, it has the smallest design range, the yellow part. And we can change this 3D figure into the contours, and it shows on the right side. So we can see if the design target is more strict, it has a smaller design range. And if we fix our acceleration target and change our displacement target to du equals to 55 centimeters, 50 centimeters, and 48 centimeters, we can see from the 3D figures that for Dmax smaller than 55 centimeters, it has the biggest design range, the blue area plus the red area and the yellow area. And for Dmax smaller than 50 centimeters, its design range will be the red area plus the yellow area. And for the most strict Dmax smaller than 48 centimeters, it has the smallest design range, yellow part. And the right figure will be the contour of the 3D figure. The next part will be the parametric study. So we want to discuss if we change some of the parameters of our system. So how does it affect our design range? So the first discussion will be the deviation of the damping ratio. So this design range is the original structure's design range. If we increase the structure's damping ratio by 15% and decrease it by 15%, we want to see how its design range change. So we can see from the results that for smaller damping ratio, we can see that the demand of the alpha 1 and alpha 2 value is bigger, and the range is smaller. And we can see that alpha 1 and alpha 2 value is bigger is because the structures provide less damping, and it depends on the displacement restraint mechanism more. So these two values have to be bigger. And the second part will be the deviation of the period. So this is the original design range, and we increase the structure's period by 15% and increase it by 15%. So we can see from the results that for a smaller period, the alpha 1 and alpha 2 value is smaller, and it has a smaller range. It is because for the smaller period, it means the structure is stiffer. And with the stiffer structure, if the value of alpha 1 and alpha 2 is too big, then the acceleration response can be very big. So the result is alpha 1 and alpha 2 value is smaller. The last part will be the deviation of the earthquake PGA. So this is the original structure's earthquake PGA. We increase it by 15% and decrease it by 15%. And we can see from the result for smaller PGA, it means that the earthquake is smaller, so the alpha 1 and alpha 2 value can be bigger, and it has a larger range. Since the earthquake is smaller, the available alpha 1 and alpha 2 can be big, and the acceleration response will not be too big. And if the PGA is increased by 15%, there is no available design range. So we can say that actually this design range is very sensitive to the PGA. So here are the conclusions. So first, in our thesis, a complete diagrammatic design procedure of the retrofit design by FPB and LRB systems are proposed. And also the whole process of isolation retrofit design, including the seismic evaluation, the system design, detailed design, and design check is provided. The third is a retrofit example of a real brick structure, Datun Elementary School, is provided for people in the engineering field to refer to. And next, for the displacement restraint mechanism, you can see that this mechanism really works while its parameters are properly designed. And we know that the design procedure and design range of the displacement restraint mechanism are demonstrated. And the sixth is that the sensitivity of the displacement restraint mechanism over the damping ratio, structural period, and PGA are discussed through parametric study. And at last, we know that the casualties caused by the near-fault earthquake could be effectively averted by the displacement restraint mechanism. Thank you, and this is my oral presentation.